So today we're looking at 6.3, which is optimization problems. That's on pages 273 to 280 in your text. Our curriculum outcome is to demonstrate understanding of the application of derivatives to solving problems including optimization, rates of change, and related rates. And our lesson objectives, number 1, to be able to identify an optimization problem. Number 2, to be able to set up an optimization problem that has more than one step to it, which is most of them, by the way. And number 3 is to be able to solve an optimization problem. So an optimization problem is a problem in which you are asked to either maximize or minimize something. And so some examples of that, you might be asked to maximize or minimize the cost of something, the volume of an object, or the area of an object, etc. And knowing that the first derivative gives you the slope of the tangent line, and knowing that max and mins, which is what optimization is about, are found by setting the first derivative equal to 0 will help you immensely. So we did this stuff in graphing, but it also comes in handy when we're talking about some actual real life situations. So you need to follow these general steps. Note they may vary per question, but this is sort of the idea behind it. So number 1, you need to know what you're trying to maximize or minimize. Number 2, if you can, draw a diagram. Number 3, you need to find an equation that describes a situation for what you're trying to maximize or minimize, and this is called the objective equation. Number 4, if necessary, you might have to find a second equation that you can substitute into the objective equation, and you'd only do that if this objective equation has more than one variable that you don't know. Number 5, once you have an equation with a single variable, take the derivative, make it equal to 0, and solve for your variable. And number 6, make sure to check your answers and answer the actual question that is asked. A lot of times people will find the first derivative, find out what x equals, and not actually answer the question. So make sure you do that as well. So a rectangular sheet of paper of dimensions 18 centimeters by 25 centimeters is to be made into an open box by cutting out equal squares from the corners and bending up the flaps. Find the length of the cutout squares so that the volume of the box will be a maximum. And what will the maximum volume be? So first we need to identify what we're trying to maximize or minimize, and that's volume. So we know right off the bat we're going to need an equation for volume. And it's of a box, so it's going to be length times width times height. So if we draw this sheet of paper, we've got 25 by 18 centimeters, but we're taking out a square on each corner. Now that square is going to have side lengths of x and x all the way around. So when we're talking about the volume of a box, that means that we have a box that looks something like this. And we need these side lengths. So this one isn't going to be 18 centimeters, but it's 18 centimeters minus that x and minus that x, so 18 minus 2x. And this one here would then be 25 minus 2x. And then the height of the box is going to be the length of one of those squares. It's just going to be x, because that's what you're folding up, a height of x. So our volume, we can now write this as v of x, because it's volume in terms of the variable x. Is your length times your width times your height? Well, that's 25 minus 2x times 18 minus 2x times x. And when you do all the work and you multiply that all together, you get your v of x being 4x cubed minus 86x squared plus 450x. So hopefully you recognize this as a cubic function, which means that it can have a maximum value, or it could have a minimum value. This one's probably just going to have a maximum volume. And that's going to be at where the first derivative equals 0. So we need to find out what our first derivative is. And that's 12x squared minus 172x plus 450. Now the easiest way to solve this thing is just by plugging it into the quadratic formula. And when you plug that into the quadratic formula, you get two answers. You get x equaling 10.9 centimeters, and you get x equaling 3.4 centimeters. You don't need to use roots. You don't need to use exact values in this case, because we're looking for how long the square has to be. Now, hopefully you can recognize that if we say that x equals 10.9 centimeters, you can't take 10.9 away from 18 twice, because that's like, that's really close to 21, right? Or 22 centimeters. That you can't take 22 centimeters away from 18. So we're going to discard that answer. We only have one answer. So each of these squares need to be 3.4 centimeters long. Now the second part of this question says what is the maximum volume going to be? Well, that's if we plug in 3.4 into our volume equation. So we go back to the original volume equation. And now it could be this one, or this one. But we go right back to it and we plug in 3.4. And when you do that, you get a maximum volume of 6,393.1 centimeters cubed. So all that's saying is that we can now use calculus to answer questions like this, where before we weren't able to do that. And it's really quite handy if you're trying to maximize or minimize something. So here's our second example. It says a farmer has 1,000 meters of fence and wishes to enclose a rectangular plot of land. The land borders a river and no fence is required on that side. What should the dimensions of the rectangle be in order to have the largest possible area? What will this maximum area be? So again, we need to identify what we're trying to maximize or minimize, because that's the equation that we're going to take the derivative of. And so we're trying to find the largest possible area. So that means that at some point we're going to find the area, and that we know is length times width. So drawing a picture, it says there's a river and that there's a rectangular plot of land. So if we called this side X, this side could be called Y. So now we have area equals length times width, which was X times Y. Now the problem is we still have two variables here. Now we need to get only one variable. So we have this 1,000 meters of fence. Now 1,000 meters of fence is going to be 2X plus Y, because that's how long the fence is going to be, and there's 2 X's and 1 Y lengths of fence. So now what we can do is just solve this equation for Y. And now we can make a substitution. We can plug this 1,000 minus 2X into the area equation. So now we can call this A of X, because we will only have X's in there. So we get A of X equaling X times 1,000 minus 2X. Well, we know that if we multiply that through, we get 1,000x minus 2x squared. So there's our area equation. Now at some point, you could take this x and we could increase the length of it. That would just make y shorter. And at some point, we're going to find our maximum area. And that's going to be if we take the first derivative. So we take the first derivative, that's 1,000 minus 4x. And then we set it equal to 0. And that tells us that 1,000 is equal to 4x, so x is equal to 250. Well, if x is equal to 250 meters, then that means that y is going to have to be the remainder, so y is going to be equal to 500 meters. So it said, what should the dimensions of the rectangle be in order to have the largest possible area? Well, it should be a 250 by 500. But we've answered that first part. And then the second part says, what is that maximum area? Well, we go back to our area equation, A of X. So we're going to find A of 250. And when we do that, we find that the area is going to be 125,000 meters squared. Now the other way to do it, since we found these two dimensions, you could just go 250 by 500. You'd also get 125,000 meters squared. So here's our last example. It says a rectangular sheet of metal, 8 centimeters wide and 100 centimeters long, is to be folded along the center of its length to form a triangular trough. So in order to maximize the carrying capacity of the trough, which was the volume, what should the width of the trough be at the top? You may assume that the carrying capacity is maximized when the cross-sectional area is maximized. So let's take a look. If we're going to draw this thing, we're basically drawing a long trough. And it said that it's 100 centimeters long, and the whole thing was 8 centimeters wide, but we folded it in half. So that means that each of these sides is 4 centimeters long. So it says we're going to try and maximize the volume. And the volume of this sort of thing, now this is a triangular prism, so the volume of this sort of thing is just this cross-sectional area multiplied by the length. So the cross-sectional area is half times the base times the height of a triangle, because that's what our cross-sectional area is, multiplied by the length of this thing. Now we have a lot of variables here. We can't have all those variables, but we do have a half base times height, and the length we know is 100. So that's okay. So we're down to 50 times base times height. We only need one variable there. So what we're going to do is take a look at this picture. So we've got 4 centimeters And we know that there's this base here, and we know that there's a height there. Now, it says in order to maximize the carrying capacity of the trough, what should the width of the trough be at the top? So that means we want to be left with B's only. So that means I'm going to have to find out what H is equal to here. Well, if I do that, if I take a look at this in terms of a right triangle, I can call this H, I can call this 4, and this is half of what B is. So if I'm going to solve for H here, because I only want B's in this equation, if I'm going to solve for H, I'm going to use the Pythagorean theorem, which is H squared plus a half B squared equals 16. That should be a half B in the brackets. So that means H squared is equal to 16 minus a half B squared is a quarter B squared, sorry. And that means H is equal to the square root of 16 minus a quarter B squared. So now I can take this and plug it into this equation. So I'm down to one equation with one variable. So we've got V equaling 50 times B times the square root of 16 minus a quarter B squared. So now we've got this equation for volume. Volume is equal to 50B times the square root of 16 minus a quarter B squared. So if we're trying to maximize the volume, that means we're going to find the first derivative of this thing. But the problem is that we don't like square roots when we're taking derivatives. So we got 50B times 16 minus a quarter B squared raised to the power of a half. Now when we take the derivative of it, we have to use the product rule. Product rule says we take the derivative of the first thing, which is 50, and we leave the second thing, which is 16 minus a quarter B squared to the power of a half, plus the first thing, which is 50B, multiplied by the derivative of this thing. Well, the derivative of this thing is when we bring down the exponent using the chain rule. So we have a half multiplied by 16 minus a quarter B squared to the power of negative a half now, multiplied by the derivative of whatever's inside, and whatever's inside is a negative quarter times B squared. So if I bring the 2 down, that becomes a negative half B. So it looks like a little messy, but you just have to remember our derivative rules. So now we can take out a greatest common factor. That's going to be 50, because there's a 50 here and here, and we're going to take out a 16 minus a quarter B squared to the smallest exponent, which is a negative half. And what we're left with is this. If we take out the 50, we took out 16 minus a quarter B squared to the negative half, we're left with 16 minus a quarter B squared. And now we took a 50 out of here, so it's gone. We took out this whole thing, so we're left with another negative. A half times a half is a negative quarter B squared. So V prime is equal to 50 times 16 minus a quarter B squared to the negative half, all multiplied by 16. So if I had a negative quarter B squared, I took away another negative quarter B squared. That's a negative half B squared. And that means V prime is equal to 50. I'm going to move this thing with the negative exponent down to the bottom. So I still have 16 minus a half B squared here. And now I have 16 minus a quarter B squared to the power of a half on the bottom. Now what I'm doing is I'm going to set this derivative equal to 0. And when I do that, this bottom part, if I were to multiply it up over here, I'm just multiplying it by 0. So the bottom part is really irrelevant to us. So that whole mess with the bottom is now kind of gone. We can ignore it because it has nothing to do with how we're going to solve for B. I'm going to divide both sides by 50. If I divide this by 50 and that by 50, I get 0 still. So now that 50 is also out of the way. So I just get a very simple equation to solve, 16 minus a half B squared. So if I move the half B squared over to the left-hand side, and that equals 16, that means B squared equals 32 by multiplying both sides by 2. And it's asking us for the width of the top, so that's just the square root of 32, and the square root of 32 is 5.66 centimeters. So you just need to be careful when you're creating this equation, and don't get freaked out when you're taking the derivative, because in the end, a lot of good things usually happen. If it's anything in the bottom gets multiplied by 0 on the left-hand side, so it just disappears. And if this 50 is just a constant, when you divide both sides by 50, it also disappears. So sometimes you're going to be left with a nice, rather easy equation to solve for. So in summary, you need to know some basic formulas in order to help you write your objective equation. So things for area, equations for volume, etc. And there's going to be some cost questions that you're going to need to know as well. If you find that you are unable to write an equation with only one variable, you are most likely needing to take what we call a little side trip in order to make a substitution. We did a few of those. So you might need a whole nother equation, like the perimeter one. You might use the Pythagorean theorem like we did with that last example, or even the concept of similar triangles and using ratios to help you eliminate that extra variable. And make sure to take the derivative of your finished formula, set it equals 0, and solve for your variable. And that's really important. So your assignment is on pages 277 to 280. Good luck, and we'll see you in class.